Good morning, everyone. We have done the definition of fundamental group, and we have proved that if a space is path connected space, then the fundamental group is independent of the base point. So now we will do simply connected spaces, and we will find out the fundamental groups for simply connected space. So firstly, we define simply connected space. A space is said to be simply connected if first of all it is path connected space, and if its fundamental group is trivial group for any point of the space. So space is called simply connected if it is path connected and its fundamental group pi1 x x naught. This is trivial group. Trivial group means if it is a group with only one element, namely the identity element for each x. We can say that this fundamental group is trivial group for some point x naught, because we know when the space is path connected, the fundamental group is independent of the base point. So if it is trivial for only one point x naught, then it is trivial for all the points x naught. So in this case, we will write pi1 x x naught is 0, because we are assuming that pi1 x x naught is trivial and it contains only identity element. So we will assume that identity element to be 0. So now we will prove that in a simply connected space, any two paths having the same initial and final points, they are homotopic. I will use the abbreviation SC for the simply connected space. In a simply connected space X, any two paths having same initial and terminal points are homotopic to each other. So let us prove this. Let us take any two paths alpha and beta with endpoints x0 and x1. Let alpha and beta be the paths with same endpoints. Say the endpoints are x0 and x1. Then we define this path alpha star beta curl. Alpha star beta curl, this is alpha star, the reverse of path beta. Reverse of beta curl is here, reverse of path beta, or we can use beta bar. Alpha star beta bar. This is beta bar is reverse. Now because alpha is a path, let us say this point is x0, this is x1. Alpha is this path from x0 to x1, and say this is path beta from x0 to x1. So this path alpha star, the reverse of beta, which is beta bar, that is defined because uh, for the product of two paths, we need only the end point of the first path should be equal to starting point of the second path. End point of alpha is x1 and end point, starting point of beta bar, that is also x1. So this product is well defined basically. And this is a loop because the starting point of this path is x0 and ending point is also x0. So this is a loop at point x0. Now, because the space is given to us is a simply connected space, and we know in a simply connected space, the fundamental group is a trivial. It contains only identity element. That means any path which is a loop based at x naught, that should be homotopic to the constant path based at x naught. So it means alpha star beta bar should be path homotopic to the constant path based at x naught. It means alpha star beta bar, the homotopy class, path homotopy class of this is equal to path homotopy class of ex naught, which means this path homotopy class into path homotopy class of beta. This is ex naught star beta, which means alpha star beta bar star beta. This is beta because ex naught star beta is beta. So this is alpha equals to beta. Now we are proving that classes of homotopy classes of paths alpha and beta, they are equal. It means alpha and beta, they are path homotopic to each other. So this we want to prove. Now we will prove that fundamental group is a topological invariant of space X. Topological invariant means if two spaces are homeomorphic to each other, then their fundamental groups are homomorphic to each other. So firstly we define homomorphism induced by a continuous map. So let us say we have a continuous map H from X to Y, and this continuous map carries point x naught to y naught, this x naught of the space x to point y naught of space y. So we write like this: h of x naught to y naught. So when we write this, h is a function from x naught to y naught. It means h is a continuous mapping from x to y, which takes x naught to y naught. And if f is a loop, let us take f, which is a loop in x based at point x naught, then what is this h circle f? The composition map. Then this will be a loop in space y, and it will be based at y naught. So we can see, let us say this is a space x, this is y. Now we have a mapping h from x to y, which takes point x naught to point y naught here. Now if we take a loop here, let us say this is the loop f based at point x naught, then h circle f, that will be a loop based at point y naught. Because if f is a loop, then basically f is a map from I to x, such that f of 0 and f of 1, they are x naught. Then what is h circle f? F is a mapping from I to x and h is a mapping from x to y. Then it will be mapping from I to y, such that h circle f of 0, it is h of f0, that means h of x naught, and that is y naught. Similarly, h of f at 1, this is also y naught. So this is a loop in space y which is based at point y naught. So now we define homomorphism induced by this continuous mapping H. So now we take H is a continuous map from x naught to y naught. So we define H star from pi1 x naught to pi1 y naught. Now we define this mapping by H star of homotopy class of path F. This is homotopy class of path H circle F. Now here we are taking the fundamental group pi1 x naught, and we are taking F to be a member of this group, which means F is a path in space X based at X naught. And we know whenever F is a path in X based at X naught, H circle F is a path in Y based at Y naught. So this homotopy class belongs to this fundamental group. So this mapping is well-defined mapping, and this mapping is called homomorphism induced by H. Relative to base point X naught. Now we will prove that this mapping is well defined. So let us take two paths F and F dash. Let these be path homotopic to each other, and their paths based at point x naught. And let us assume F is the homotopy between F and F dash. Then H circle F and H circle F dash both are paths in space Y based at point Y naught, and we know whenever these two are homotopic and we compose these two mappings with the same mapping H, then these two will also be homotopic to each other, and the homotopy here will be H circle F. So if this is a homotopy between F and F dash, then H circle capital F, that is a homotopy between H circle F and H circle F dash. So it means this is well-defined mapping. And secondly, we will prove this is a homomorphism. And to prove this is a homomorphism, basically, we have to prove that H star F into H star G. So here into means product, because H star F is a homotopy class, and this is also homotopy class. So homotopy classes, their product is denoted by star. So it will be H star F star G. So we want to prove this thing. And that means we have to prove this. H circle F star H circle G. This is H circle F star G. And we have already proved this result, that H circle F star H circle G, this is equal to H circle F star G. So from this result, we can easily prove this result. So this is a homomorphism. Now this homomorphism, this does not depend only on the map H, but it is dependent on the point, base point X naught also. So we call this homomorphism induced by H relative to base point X. So if we take two different points x0 and x1, let us take two different points x0 and x1 in space X. Then we symbolize H star for two different mappings. So then we have one H star is from pi1 x0 to pi1 y0, and then other H star is from pi1 x1 to pi1 y1, where y1 is the image of point x1. So in that case, we will differentiate both the H star mappings by these symbols, hx0 star and hx1 star. Now, hx0 star is the mapping which takes x to y, and which is from the fundamental group based at point x0, and hx1, this is homomorphism induced by H relative to the point x1. So now we come to this theorem, which proves that if H is a mapping from XX naught to YY naught, and K is a mapping from YY naught to ZZ naught, and suppose these two are continuous mappings, then first of all we have to prove that K circle H star, this is equal to K star circle H star. And second thing we want to prove in this theorem, that if I is the identity map from XX naught to XX naught itself, if this is identity map, then the homomorphism induced by I, that is also identity, which means then I star, this is also identity map, identity of fundamental groups. So let us prove this, and the proof is very trivial because K circle H star at homotopy class of F, by definition it is K circle H circle F, homotopy class of this. And by associativity we can say, or we come to right hand side. Now this is the left hand side, and now we will take the right hand side and we apply firstly H star on this F, and we will get H circle F, and then we apply K star, then we will get this H K circle H circle F. And by associativity we know this K circle H circle F, this is homotopic to K circle H circle F, so their homotopy classes are same, it means these two are same. So we can say that K circle H star, this is K star circle H star. And for the second part, that is very trivial because I star at F, by definition it is I circle F, and I is the identity map, so I circle F is just F. So I star of F is F, so it means I star is identity map. If H is a homeomorphism from XX naught to Y naught, which takes the point X naught to Y naught, then H star, this is an isomorphism of the fundamental group pi1 x x naught with pi1 y naught. Now this result proves that if we take H to be a homeomorphism, which means if X and Y are homeomorphic spaces, then H star is isomorphism, which means these fundamental groups are isomorphic to each other. So this result proves basically that fundamental group is a topological invariant. Means if two spaces are topologically equivalent or homeomorphic to each other, then their fundamental groups are algebraically equivalent. Then their fundamental groups are basically isomorphic to each other. So this result can be asked in this way: if two spaces are homomorphic to each other, then their fundamental groups are isomorphic to each other. And in other words, this is a topological invariant or topological property. So in this case, we are taking H to be a homeomorphism. It means H is a bicontinuous bijective map. So we can take K to be the inverse of H. So let K be inverse of H. And if it is inverse of H, then it is basically a mapping from YY naught to XX naught. And in the previous result, we have proved that K star circle H star, this is equal to K circle H star. And if K is inverse of H, then K circle H is identity map. So it is I star, and I star is identity. So here we are proving that K star circle H star is identity map. Similarly, we can prove that H star circle K star, this is also identity map. So here we are saying basically H and K are continuous maps. So H star and K star, they are homomorphisms. H star is from pi 1 x 0 to pi 1 y 0, and K star is from pi 1 y 0 to pi 1 x 0. And both the compositions K star circle H star and H star circle K star, they are identity. So it means H star is inverse of K star, or in other words we can say H star is an isomorphism, and this is isomorphism from pi 1 x 0 to pi 1 y 0, and which completes the proof of this result.